Hello my dear friends, I am Shubham from LearnoHub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. तो चलो शुरू करते हैं. So, as we all know which chapter we are studying, chapter number 1, periodic properties and variations of properties, physical and chemical. And up to this video, we have covered almost all the concepts of this chapter, but one special thing of this chapter is remaining, which is special reference to the group 1, group 2, group 17 and group 18 elements. Okay, so this topic we are going to study in this video, and after that we are quickly going to solve the previous year questions which has been asked in your examinations. Okay, so then without wasting time, let's start and let's rock. Okay, so how we are going to study this group 1, group 2, group 17 and group 18 elements. Okay, so what we can do is, since group 1, group 2 and group 17 elements have almost the properties which can be studied in comparison to each other. Okay, group 18 elements are like quite different from all these elements. Okay, so what we are going to do, we are going to study group 1, group 2 and group 17 elements properties, okay, in one go, and later on after this we are going to see the properties of group 18 elements. Okay, so let's start with first the elements which are present in group 1. Okay, so we have to study the alkali metals in special reference. Okay, alkali metals means lithium, sodium, potassium, rubidium, cesium, francium. Okay, so it doesn't include hydrogen. So when I'm talking about group 1, we are only focusing on the alkali metals except hydrogen. So here elements are just now I told lithium, sodium, potassium, rubidium, cesium, francium. I have also told you the trick, LINAC, RBCs, Fra. Okay, then alkaline earth metals elements, same way I have also told you the trick, beryllium and magnesium you can remember in the one go. Calcium, strontium, barium are Dobrainer's triad, and then barium rhyming is radium. Okay, so barium, radium, beryllium, magnesium, calcium, strontium, barium, radium. And then halogens, fluorine, chlorine, bromine, iodine, astatine. Every halogen's name in the ending has "ene." Okay, so just remember it in a one go. Okay, in one rhythm. Now next is occurrence. So how we find these elements in nature? All these, okay, alkali metals, alkaline earth metals as well as halogens are found in combined state. Okay, so what does this mean? Combined state means they are found in the form of compounds. Okay, the compounds of the particular metal. So suppose sodium, if we take example of sodium, we cannot find sodium in a free state. Okay, we cannot find in nature sodium atom. We always could find the sodium in the form of salt, NaCl, right? So in this way, these all elements are found in the combined state. Okay, we find the compounds of this elements, okay, in nature. And why is this so? Because they are reactive in nature. Okay, they don't sit quietly. They, whenever they get opportunity to react, they quickly go and react, and once they react with some other element, they form a compound, and in this way we find them in the nature. Okay, now next is physical state. So alkali metals, you would have heard that sodium exists as solid, but it is so soft that we can cut it with knife, right? So yes, alkali metals are solid, okay, but they are soft. We can cut them with knife as well. Okay, moving on to the alkaline earth metals, they are also soft. Okay, but they say that we are harder than alkali metals. Okay, because we come after alkali metals. So yes, they are harder than alkali metals. Okay, in this way you can remember. And then halogens, we know the physical states of all the halogens. We have already studied fluorine and chlorine exists as gases. Bromine is the liquid, okay, and iodine is existing in solid state. Okay, moving ahead to the next properties, conduction. Okay, how is the conduction of all these elements? Okay, alkali metals are good conductors of electricity. Same, alkaline earth metals are also good conductors of electricity, but halogens are non-conductors of electricity. Okay, so they don't conduct electricity. Then melting points and boiling point. Okay, so we already have studied the trend of melting point and boiling point, right? When we were studying the trends of the periodic properties. After chemical reactivity, we studied the trend in the physical properties, in which the first one was melting point and boiling point. Okay, so in case of metals, what we have studied, melting point is decreasing, right? And boiling point is also decreasing. So I have shown you this example at that time as well. Lithium, sodium, potassium, these are metals. Okay, Melting point you can observe 180, after that 180, 94, and then 63. Then 1347 is the boiling point of lithium, then moving to sodium 883, and then 774. So we can observe a decrease in melting point as well as the boiling point. Okay, so at that time we just studied in general about metals. So metals show a decrease in melting point and boiling point when we move down the group, but here we took the example of alkali metals, right? So at that time only we have studied this property of alkali metals, that alkali metals melting point and boiling point decreases, okay, as we move down the group. Okay, now let's see the melting point and boiling points trend, okay, in case of halogen when we move down the group. What happens in case of halogen? At that time we have studied the trend of melting point and boiling point in case of non-metals. What happens? The melting point and boiling point increases. Okay, here is the example. See, we have seen the same example: fluorine, chlorine, bromine, iodine, melting point and boiling point. From minus 219 to plus 113, it is increasing. From minus 187 to plus 183. Okay, you can see the values as well: minus 219, minus 101, minus 7.2, and then plus 113. So it is increasing. Minus 187, then less negative, minus 34, then it's becoming positive, plus 58, and then plus 183. So boiling point is also increasing. Okay, and the example is of non-metals, which are fluorine, chlorine, bromine, iodine. So at that time only we have studied this property of the halogens as well, that their melting point and boiling points increases as we move down the group. Okay, now moving to the alkaline earth metals. So they don't show a regular trend in melting point and boiling point. Okay, but yes, again the same thing. They are saying that just like how we are harder than alkali metals, we have higher melting point and boiling points than alkali metals. Okay, so in this way you remember. Now moving ahead, atomic size. Okay, so alkali metals have largest atomic size in their period. Okay, we have already studied this when we were studying the trend of atomic size, okay, across the period from left to right. Right, we know atomic size from left to right when we move, okay, across a period, it decreases. So this means that we have already studied that the alkali metals are to the extreme left, so they would be having largest size. So yes, therefore they show largest atomic size in their period. Okay, next is alkaline earth metals. They have atomic sizes smaller than the group 1 elements in their period. Very logical, very correct. We already know this thing also, because see, when we move from left to right across a period, atomic size decreases. So alkaline earth metals would definitely have the atomic sizes smaller than the alkali metals, that is group 1 metals, okay, group 1 elements in the same period. Correct. And halogens have smallest atomic size in their period. This thing also we have studied. See, across the period, left to right, atomic size decreases. So smallest atomic size is shown by halogens, not by group 18 elements. Okay, group 18 elements actually have more sizes than the halogens, and the reason for this we have already studied, right? So the smallest atomic size is shown by halogens in their period. Next, what happens to the atomic size of alkali metals when we move down the group? Similarly, atomic size of the alkaline earth metals when we move down the group, and atomic size of the halogens when we move down the group. It's very simple. You have to just remember the trend of atomic size, okay, down the group when we move from top to bottom. What is the trend? The sizes increases, okay, and yes, alkali metals atomic size also increases down the group. Same alkaline earth metals atomic size also increases down the group, and halogens atomic size also increases down the group. Very simple how to remember the trend, how to remember their properties. Now moving on to metallic character and non-metallic character. So since these are metals, alkali metals and alkaline earth metals, we will consider metallic character for them. Halogens are non-metals, so we will consider non-metallic character for them. Okay, now here we will just see the trend of the metallic character when we move down the group for alkali metals and alkaline earth metals. So what is the trend? What happens to the alkali metals and alkaline earth metals metallic character when we move down the group? Just remember the trend of metallic character when we move down the group. That's it. So what happens? Metallic character increases, we know. And yes, alkali metals and alkaline earth metals metallic character also increases as we move down the group. They follow that trend. Absolutely, perfectly they follow that trend. Okay. Now, what happens to the non-metallic character of halogens? Okay, so just remember the trend of non-metallic character when we move down the group. What happens to the non-metallic character when we move down the group? The non-metallic character decreases, right? from fluorine, from top to bottom, it decreases, and halogens also follow the same. Their non-metallic character also decreases as we move down the group. Now, moving ahead, next is ionization energy. Okay, now what you have to remember, just the trend of ionization energy when we move across the period. That's it. So your first point for all the group elements, okay, for alkali metals, for alkaline earth metals and halogens would be very clear. Okay, so what we have to just remember, what happens to the ionization energy when we move across the period from left to right. Ionization energy increases. We have already studied, right? So see here, now if it is increasing from left to right, on the extreme left it would be the least, and on the extreme right it would be the highest. So on the extreme left, which elements are present? Alkali metals. So they would have the least ionization energies. Correct? Yes, they are having lowest ionization energies in their period. We learned the way in which we have to remember the property. Okay, or we can reach up to the property itself. Okay. Now, just now I said it increases from left to right. So the highest values would be towards the right. And see, halogens, that is group 17 elements, belong to the almost to the extreme right. Okay. So therefore they would be having the highest values of ionization energy. Here you can see in the table, see 1681, 1256, right? But their ionization energies would be lower than the group 18 elements, okay, because the highest ionization energies would be possessed by group 18 elements. So high ionization energies, they show high ionization energies but lower than the group 18 elements in their period. And now alkaline earth metals part. So we know the ionization energy increases. So alkaline earth metals would be having higher ionization energy than group 1 elements. But yes, the values of ionization energy of alkaline earth metals would also be towards the lower side only, because they belong to the left of the periodic table, right? So they have low ionization energies, but their ionization energy values are higher than alkali metals. Okay, 520 here, lithium is having ionization energy, beryllium is having 899. You can see here clearly. Okay, but more than alkali metals. Now, next is you have to just remember the trend of that particular periodic property. Here you have to remember the trend of ionization energy as we move down the group from top to bottom. Okay, and yes, that particular trend would be followed by all these three group elements. So what happens to the ionization energy when we move from top to bottom in a group? Ionization energy decreases, right? So if it is decreasing, it is same for all these three group elements. See, it decreases down the group. Okay, it decreases down the group and it decreases down the group for all these three group elements. Next is electron affinity. Okay, so alkali metals show low electron affinity values, halogens show high electron affinity values. Okay, now how you can remember this? Just try to remember the trend of electron affinity. Okay, when we move across the period from left to right. Okay, so what happens to the electron affinity? We have studied the electron affinity values increases. Okay, so this means that to the extreme left, the electron affinity values would be low. Now alkali metals are present to the extreme left, so therefore they have low electron affinity values. That's it. So in this way you can remember the things. Okay, halogens are like towards almost extreme right, so therefore they would show high electron affinity values, right? Then alkaline earth metals, we have already studied this when we have studied the topic of electron affinity, that alkaline earth metals means group 2 elements are exceptional, means they are exception. Okay, because they show irregular trend in the electron affinity values. Okay, so bus, that's it, we have to remember about them this much only. Okay, now considering the electron affinity trend down the group, you could remember these 2 points of alkali metals as well as halogens. Okay, alkali metals electron affinity decreases down the group, and same halogens electron affinity also decreases down the group. How to remember? Just try to remember the trend of electron affinity. Okay, when we move down the group from top to bottom, what happens? Electron affinity values become less and less, right? So they decrease. So that's it. You can remember in this way, alkali metals electron affinity value decreases down the group, halogens electron affinity values decreases down the group. But in case of halogen, you have to just remember the exception as well, okay, which we have already learned, that electron affinity value of chlorine is more than the fluorine. And why is this so? That reason also we have studied when we were learning the exceptions in the electron affinity. Next is electronegativity. So alkali metals show the lowest electronegativity value in their period, okay, and halogens show highest electronegativity value in their period. Okay, how to remember it? The same way, from left to right we know electronegativity value increases, right? So to the extreme left the values would be lowest. See, to the extreme left alkali metals are present and they are having lowest electronegativity values. In this way we can remember. And to the extreme right, okay, the values would be highest. So at the extreme right, okay, we know noble gases are present, but yes, noble gases don't show electronegativity, right? That's why. So which elements, which group of elements would be that there at the extreme right? It would be group 17, right? So group 17 elements would show highest electronegativity values. Yes. So in this way we can remember. Now next, alkaline earth metals. Okay, they show less electronegativity value. Now this can also be remembered from the trend only. See, from left to right it is increasing. So the electronegativity values are less because the alkali metals also belong to the left side. Okay, so low electronegativity values they would also possess, but their electronegativity values would be greater than alkali metals. See, 1.2, 1.8, that's the point, but more than the alkali metals. Next, from top to bottom, okay, in a group when we move we find that electronegativity goes on decreasing. Okay, that's it. In this way only we would remember for alkali metals, alkaline earth metals and halogens as well, the electronegativity value decreases down the group. Next is reactivity. So alkali metals are highly reactive, okay, and halogens are also highly reactive. Okay, we already know, we know the reactivity is high at the extreme ends of the periodic table. So towards the left and towards the extreme right the reactivity is high. So therefore, see, alkali metals belong to the extreme left, we know halogens belong to almost to the extreme right. Okay, so therefore they have high reactivity. In this way you can remember. And alkaline earth metals, now we have studied the trend of reactivity when we move across the period, right, from left to right. So what happens? Reactivity increases, okay, initially, then after reactivity decreases, okay, initially, then after a particular element, okay, when it becomes lowest it again starts to increase, right? So from alkali metals when we are moving reactivity is decreasing. So what would happen? The alkaline earth metals would be having less reactivity than alkali metals, right? But since alkaline earth metals also belong to the extreme left, so therefore they are also reactive, okay, but their reactivity is less than the alkali metals. See, they are also reactive but less than alkali metals, okay. Then down the group we have to just remember the trend. Now in this case we have studied the reactivity ka trend, okay, down the group for metals as well as for non-metals. So since alkali metals, alkaline earth metals, these are metals, so we would just apply the reactivity ka trend, okay, for metals, okay, and in case of halogens we would just apply the trend of reactivity for non-metals. So what is the trend of reactivity down the group in case of metals? What happens? Reactivity either increases or decreases. So when we move down the group we know reactivity increases, right? So therefore alkali metals reactivity increases down the group, alkaline earth metals reactivity also increases down the group. Now in case of non-metals we know that when we move down the group from fluorine, chlorine, bromine, iodine, okay, I am taking an example, fluorine, chlorine, bromine, iodine, so reactivity goes on decreasing, okay. So yes, in case of non-metal reactivity goes on decreasing, therefore halogens are also non-metals, so therefore their reactivity also decreases down the group because halogens follow the trend of the reactivity in case of non-metals, okay, the trend of reactivity of non-metals. Now next is reaction with water and acids. Now this is interesting part. So alkali metals react vigorously with water as well as acid and they liberate hydrogen gas, okay. So see, we can just remember this with the help of the reaction itself. So I am taking an alkali metal, okay, sodium. Now when it reacts with water it forms sodium hydroxide, okay, and it liberates hydrogen, okay. So two water molecules are needed in order to balance this reaction. Same way when sodium is reacting with acid, okay, suppose HCl, okay, what it forms? 2 sodium and 2 chlorine, Okay, it combines to form 2 NaCl and 2 hydrogen releases in the form of H2. In this way also you can remember. Okay, the reaction happens as Na plus HCl gives NaCl plus H2, but I'm just sharing you a trick to remember the reactions. Okay, so what is happening? See, hydrogen gas is released in case of alkali metals, and these reactions, okay, with water and acid are vigorous. Okay, they are very tremendously explosive. Now next is alkaline earth metals. So they also readily react with water and acids, and they also liberate H2. So I'm taking the example here. See, if I am reacting Mg with water, what would happen? MgOH twice, magnesium hydroxide is formed and H2 is released. Okay, so 2 water molecules, okay, and the reaction is balanced. 4H, 4H, 2O, 2O and 1 Mg. Similar way, when the alkaline earth metals react with acids, okay, they also release the dihydrogen. They also release hydrogen gas. Okay, so how they release hydrogen gas? Mg combines with chlorine, 2 chlorine becomes MgCl2, and then 2 hydrogen get released as H2. Okay, in this way you can remember that yes, both the alkali metals and alkaline earth metals react with water and acids and they liberate H2, but the reaction of alkali metals is more vigorous, and the reaction of alkaline earth metals, okay, they also react readily, okay, but not as vigorous as alkali metals. Okay, next, halogens. So halogens generally don't show any reaction with water as well as dilute acids. Next is reducing and oxidizing agent. So alkali metals are strong reducing agents. Okay, now we have already studied that metals are good reducing agents. Okay, metals behave as reducing agents, and we have also studied that more is the tendency to lose the electron. Okay, to lose the electron, stronger is the reducing agent, right? Now here alkali metals, okay, they have very high tendency to lose the electron. How? Why? See, alkali metals have only one electron in their outermost shell. Okay, I'm taking an example of, suppose, sodium. Okay, so this is the nucleus of sodium, this is the sodium atom. Okay, first shell 2 electrons, second shell 8 electrons, and third shell 1 electron. Now sodium has strong tendency to lose electron because after losing this electron, it would have the outermost shell which will have 8 electrons. Okay, so that this means that its outermost shell has attained the octet. Okay, and it becomes stable. See, 2 8, so it is attaining the configuration of neon, right? Neon is also having configuration 2, 8. That's why it is having very strong tendency to lose this electron. And since it is having very strong tendency to lose the electron, therefore alkali metals are strong reducing agents. Okay, similarly halogens are strong oxidizing agents. Why? We have already studied that non-metals behave as oxidizing agents, correct? And same, more is the tendency to gain the electron, okay, more is the strength of the, or more strong is the oxidizing agent. Okay, this also part we have studied already. So now in case of halogens, they have very high tendency to lose, high tendency to gain electron. Why is this so? See, I'm taking an atom of halogen, fluorine. Okay, so this is the nucleus, suppose, of the fluorine. First shell and second shell, 2 electrons in the first shell, 7 electrons in the second shell. So it badly needs one more electron, just one more electron, and then its outermost shell would have 8 electrons. It would attain the octet, and again it would also attain the configuration of neon, which is very stable. Okay, so it would become stable by gaining one electron. That's why it just anyhow it wants that one electron. Okay, so it has very high tendency to gain that electron, high tendency to gain the electron. Okay, so since it is having very high tendency to gain electron, so therefore it behaves as a strong oxidizing agent. Okay, now alkaline earth metals, they are also strong reducing agents. Why? Because see, they also have strong tendency to lose the electrons. Why? See, if I'm taking the example of magnesium, I know it is having electronic configuration 2, 8, 2. Once it loses this 2 electron, it also attains the same stable configuration of neon. Therefore, it also has very strong tendency to lose this 2 electron. Therefore, it also behaves, see, if it also has the very strong tendency to lose the electron, therefore, it also behaves as a strong reducing agent. Okay, but its reducing power is less than the alkali metals. Now, how we can figure out this? Why is it happening? See, just try to remember the trend of the reducing nature across the period from left to right. Okay, what is happening? So, in order to remember the trend of reducing nature, okay, across the period, remember the trend of metallic character, because we know that the metallic character trend and the reducing nature trend is exactly the same. Okay, so metallic character from left to right, what happens? It decreases, correct? So reducing nature also decreases, right? Now, since reducing nature is decreasing from left to right, see, first alkali metals would come, then alkaline earth metals are there, right? So if it is decreasing, reducing nature is decreasing, so alkaline earth metals would have less reducing nature than alkali metals. See, therefore they have less reducing power than alkali metals. Now let's see the compound formation, last property of this group elements. So alkali metals form ionic compounds with non-metals. Okay, example, see, NaCl is an ionic compound. Okay, so in this, see, alkali metal sodium is combining with non-metal chlorine. Similarly, potassium alkali metal is combining with bromine. Okay, now we will learn in detail about the ionic compounds in the next chapter itself. Okay, don't worry. Now, alkaline earth metals, they also form the ionic compounds with non-metals, like just like the alkali metals. See, alkaline earth metal magnesium, it is forming the ionic compound with non-metal chlorine. Similarly, calcium alkaline earth metal is forming the ionic compound with non-metal chlorine. Okay, now in the same way, halogens also form ionic compounds with metals, because halogens are non-metals, right? So ionic compounds with metals, example is KCl. This is a non-metal. Okay, halogen itself is a non-metal. It is forming an ionic compound KCl with metal potassium. Okay, and they also form covalent compounds with hydrogen. Okay, just like this HCl. Don't worry about the covalent compounds as well. We are going to study it in very detail in next chapter. And not only it forms covalent compounds with hydrogen, like just like HCl, it also forms covalent compounds with other non-metals. Okay, so other non-metal, for example, here is carbon. So it is forming covalent compound with carbon, CCl4. Okay, halogen and non-metal carbon. Now we have studied in detail about group 1, group 2 and group 17 elements. Now it's time to see the group 18 elements. Okay, so most of the properties of the group 18 elements we have already studied. Okay, first one is actually the elements. Which are the group 18 elements? We already know: helium, neon, argon, krypton, xenon, radon, right? And their occurrence, we also know about their occurrence, that they exist in a monoatomic state. I have already told you that helium atom, suppose for example, helium atom will not even combine with the another helium atom. Okay, it is very much happy with itself only. So in this state, okay, single atom, it is existing in a single atom state. So therefore we are saying that it is existing in monatomic state. Now since they are existing in monatomic state, they are not combining with any other element. Okay, they are not combining with any other atom of element, same element as well as other elements. So we say that, so it's very clear that they exist in a free state. Okay, they are free, they are not combined with anyone, right? And why is this so? Because of their inert nature, because they are very much satisfied with their 8 electrons. They have complete octet, no need of gaining electron, losing electron, sharing electron. That's it. Okay, now physical state, gaseous, all are present in gaseous state. We have already studied when we are studying the physical state of the elements in the periodic table, right? Which elements are having solid state, which elements are having liquid state, and which elements are having gaseous state. Okay, so all this side, the group 18 elements, we are having gaseous state. Okay, next to group 18, fluorine and chlorine, we are having the gaseous state. In this way we have studied, right? Now atomic size, we have already studied this part also, that atomic size of the noble gases are greater than the halogens of the same period. Okay, why is this so? We have already studied this thing. And also one more fact that, see, though the atomic size of noble gases is greater than the halogens, but it is lesser than the alkali metals of the same group. See, 112, neon is having the atomic size and lithium is having 152 atomic size. Okay, so it is lesser than the alkali metals of the same group. Okay, group 1 metals of the same group. And simply, it also follows the trend of atomic size. When we move down the group, atomic size increases as we move down the group. So inert gases also follow the same trend. Okay, their atomic size also increases as we move down the group. Next is ionization energy. Okay, so they show highest ionization energy in the period. Okay, so you can see here in the second period, in the example of second period elements, so you can clearly make out the highest ionization energy is 2080 and it is shown by inert gases. Similarly, in the third period as well, the highest ionization energy is 1520, it is shown by argon. Okay, now the ionization energy decreases as we move down the group. Okay, it's just simply following the trend of ionization energy when we move down the group, and we know what is the trend of ionization energy when we move down the group. Ionization energy decreases, so it is also decreasing. Okay, its ionization energy is also decreasing. Okay, next is electron affinity. So it is having positive electron affinity values. It was like very interesting thing, and we have also studied its Y as well. Okay, so if you feel that you can't recall the Y, you can just go back in that electron affinity section, okay, where we studied what is actually electron affinity and all those things, and you can just remember it. Okay, you can just understand it again. Then electronegativity does not show electronegativity. This thing also we have already studied, and its Y is also, its why is it, why they don't have electronegativity, I have already taught you. Okay, now let's move on to the interesting part. I'm going to tell you the trick for remembering the trends. Okay, now I know it takes some time to remember the trend. Okay, particular trend, what it means, whether it increases or decreases as we move across the period from left to right, as we move down the group from top to bottom. So I'm going to tell you a simple trick. By using that trick, it would be very easy for you to just figure out the trend, okay, when you are solving the questions. So very simple. Atomic size, the trend of atomic size you have to just remember. That's it. And rest all the trends you would actually figure out, because the atomic size trend, okay, the same trend is shown by only metallic character. Okay, now apart from metallic character, okay, we are having rest 4 periodic properties. Okay, so non-metallic character, ionization energy, electron affinity, and electronegativity. Okay, so these 4 periodic properties apart from metallic character and atomic size, okay, these show opposite trend to that of the atomic size. Very simple. Now we know across the period, when moving from left to right, atomic size smaller the atoms become, so atomic size decreases, right, when we move from left to right in a period. Now this means that metallic character also decreases, and we know that since metallic character is decreasing, so reducing nature also decreases. Okay, we have already studied the correlation, they are having the same trend. Now apart from metallic character, now non-metallic character, ionization energy, electron affinity, and electronegativity, all of them increases as we move across the period from left to right. Okay, now same you would apply the concept for down the group. Okay, and then just try to find out. Very easy. It would be very easy for you now to remember the trends. Now let's solve some previous year questions which have been asked in your exam. So the first one is asked in 2019. Study the extract of the periodic table given below and answer the questions that follow. Give the alphabet corresponding to the element in question. Do not repeat an element. Okay, so first what we can do is, let's just write which element is that particular alphabet. Okay, so A, we know here the position is occupied by hydrogen. Okay, in the periodic table I have already told you to keep a rough structure of periodic table in your brain, right? So there starts from hydrogen, we go to helium, lithium, beryllium, then comes boron, carbon, nitrogen, oxygen, right, then fluorine, and below fluorine there is chlorine, and after chlorine there is argon. Okay, and yes, here the third period starts from sodium, then B would be magnesium. Okay, so we have just named it. Now let's solve the questions. Okay, it would be now easier for us. Which element forms electrovalent compound with G? Okay, so what is G actually? G is chlorine, right? So which element would form electrovalent compound with chlorine? First of all, let's see. Chlorine is a non-metal, right? Let's try to correlate it. Now just now we have studied that alkali metals and alkaline earth metals form electrovalent compounds or ionic compounds, right? These are also called as ionic compounds with non-metals, right? So this means that who would combine with chlorine then? Alkali metals or alkaline earth metals. Now out of these given elements, which of the following, which you would find, which of the element is alkaline earth metal or an alkali metal? Okay, so hydrogen is not an alkali metal. That's it. Then remaining no element is from alkali metals. They have given us. Then alkaline earth metal. See, magnesium. We got our answer. Okay, so the answer is, right answer is of this question is magnesium. Okay, now second question is like which ion would migrate towards cathode. Once we would study electrolysis in detail, we would answer that question. Okay, but for your understanding reason, the ion which would migrate to cathode, okay, is cation. Okay, cations migrate to cathode. Okay, you can remember in this way. So out of this, hydrogen forms H plus, and this H plus cation, okay, migrates towards the cathode during electrolysis. Okay, so the answer here is H plus. Next, which non-metallic element has valency 2? Okay, so it's very simple to find out. Non-metallic element, they have said us, these are metals. Okay, magnesium is metal, hydrogen is a non-metal, but it doesn't have a valency of 2. Boron, nitrogen, we know boron doesn't have the valency of 2, nitrogen doesn't have the valency of 2. Why? Because see, boron's electronic configuration is 2, 3, right? Carbon's 2, 4, nitrogen's 2, 5. So see, its valency is 3. Here the valency of nitrogen is 3. Okay, we know 8 minus 5. I did just 8 minus 5. I got the valence of nitrogen because the number of electrons in the outermost shell is 5. Okay, so we do 8 minus 5, 3. Then oxygen 2, 6. And yes, 8 minus 6 is 2. And oxygen, yes, it is an non-metallic element. Okay, so first of all, non-metallic element is matching, and valency 2. It also has valency 2. Okay, apart from it, chlorine has valency 1. We know because it has 2, 8, 7 electronic configuration. It just needs 1. Or we can also say that 8 minus 7 is equals to 1. Okay, argon's 0 valency. Okay, so answer is oxygen. So oxygen means we are going to write the alphabet. Okay, sorry, here I have written magnesium, but we have to write the alphabet corresponding to the question. Okay, alphabet corresponding to the element in the question. So what alphabet is corresponding to magnesium? B. So answer would be B. Okay, here the answer would be A, right? H is A, and then here the answer is oxygen and its alphabet is E. So answer is E. Which is an inert gas? Very simple, we know argon, right? So answer would be F. Okay, so this question was asked in your examination in 2018. So what is the question? In period 3 of the periodic table, element B is placed to the left of the element A. Okay, so suppose this is, I have written here element A. Now element B is placed to the left of element A. Okay, so left is this, right? Left, this is right. So left of element A, element B is placed. Now what they are saying, on the basis of this information, choose the correct word from the brackets to complete the following statements. Okay, so the element B would have lower/higher metallic character than A. We have to just apply the logic of, since these are the third period elements. Okay, we have to just apply the logic of the periodic trend. Okay, how it is varying when we move from left to right across a period. Okay, so metallic character, it decreases from left to right. Okay, so if it is decreasing, A would have less metallic character than B. Now what they have said, the element B would have, so A would have less metallic character, B would have more metallic character, right? So element B would have more means higher, right? So higher metallic character than A. Simple. Now element A would probably have lesser/higher electron affinity than B. Okay, so electron affinity trend is irregular, we know that. That's why they are saying probably. But yes, generally electron affinity, what trend it shows? From left to right, electron affinity increases, right? So now A would have more electron affinity than B. Okay, if it is increasing. Now what they are asking us, the element A would probably have more, right? More means higher electron affinity than B, correct? then element A would have greater / smaller atomic size than B. Same. So atomic size variation, atomic size decreases, right, when we move from left to right. So here A would have less atomic size than B. Okay. Now the element A would have less means smaller, right? So smaller atomic size than B. Next, okay. So this question A, it has a sub question A, B, okay, and C and D are also there. And this question was asked in your exams in 2016. Okay. So metals are good dash oxidizing or reducing agent. Okay, we already know. We have just now studied metals are good reducing agents, right? Now, why is this so? They are asking us the why, because they are electron dash. Okay, so we know reducing agents are the elements which have tendency to lose electron, right? And since metals have the tendency to lose electron, we say that metals are reducing agent, right? So losing an electron means, is it accepting or donating the electron? Yes, it is donating, right? They are losing, right? So they're losing, they are donating the electron. So metals are behaving like donors, electron donors. So because they are electron donor. Okay. An element with atomic number 19 will most likely, atomic number 19, which element? Potassium. Okay, will most likely combine chemically with the element whose atomic number is. Okay, so most likely combine chemically with. Okay, they are asking us most likely. So let's first figure out the atomic, means the elements, okay, whose atomic numbers are given. So by looking at the atomic number, let's just try to write the elements. Okay, so 17 atomic number is possessed by, or chlorine is having 17 atomic number, right? Similarly, sodium is having 11 atomic number. 28, okay, it's nickel, okay, but no worries. Okay, you after 20 we have to just we should be exposed to the entire periodic table, but no need to worry about the elements beyond calcium. Okay, now, so this is out of question, don't worry about this, it won't be our answer. Then 20 is our calcium. Okay, so apart from now the options are chlorine, sodium or calcium. Okay, from these three we have to choose. Now sodium and calcium, okay, potassium is in the same group as that of the sodium, so it won't react with it. Okay, they are having same characteristics. Okay, calcium also, okay, this is also a alkaline earth metal, so it won't most likely react with calcium. Okay, because it is also a metal, but see, chlorine, and just now we have studied the alkali metals, okay, they form ionic compounds with non-metals, right? So chlorine is a non-metal, and potassium would form ionic compound KCl with chlorine. Okay, so most likely it would combine with chlorine. So our answer is 117. Okay, the C part, rewrite the following sentences by using the correct symbol greater than or less than in the blanks given. First is the ionization potential of potassium is dash that of sodium. Okay, so first let's locate potassium and sodium. Okay, so third period sodium, fourth period potassium, right? And group number 1. Now they are asking us whose ionization potential is more. Okay, or in this sentence we have to just figure out first whose ionization potential is more or whose ionization potential is less. So how we can figure it out? So we know these are group 1 elements, right? And we know when we move down the group from top to bottom, what happens with the ionization energy? Ionization energy decreases. Okay, so how am I able to figure it out very quickly? I've just used the trick. Okay, atomic size increases as we move down the group, right, from top to bottom, we know. So I have told you, rest all, apart from metallic character, all the characters, okay, all the properties, the remaining 4 properties, electronegativity, electron affinity, and ionization energy, and non-metallic character, all will show the opposite trend. So ionization energy will show the opposite trend to that of the atomic size, right? So opposite is decrease. So from top to bottom when we move, ionization energy decreases. Okay, if it is decreasing, so potassium would have less ionization energy than sodium, right? Then the next element to the potassium, okay, rubidium, okay, it would have less ionization energy than the potassium, right? So in this way, so potassium is having less ionization energy than sodium, right? So the statement, we can complete the statement. See, the ionization potential of potassium is less than that of the sodium. Okay. Similarly, second one is the electronegativity of iodine is dash that of the chlorine. Same way. Okay. Iodine, let's look at iodine. It is here. So fluorine, chlorine, bromine, iodine, right? So chlorine is here, iodine is here. Okay, in the same group. Now apply the trend of electronegativity down the group. Okay, so just now I have told you atomic size is increasing, we know. Okay, when we move down the group, so electronegativity is opposite, right? Electronegativity's trend would be opposite, it would be decreasing, right, when we move down the group. So iodine's electronegativity would be less than the chlorine. So see here, the electronegativity of iodine is less than that of the chlorine. Next sub question is fill in the blanks by selecting the correct word from the brackets. If an element has a low ionization energy, then it is likely to be metallic or non-metallic. Okay, so see, if that particular element is having low ionization energy, this means that energy required, okay, to remove the electron is low, right, is less. Now, if the less energy is required to remove the electron from that element, okay, from the atom of that element, so this means that that particular element is also somewhat willing to lose the electron, right? Okay, that's why less energy is required. So if that particular element is somewhat willing to lose the electron, then this means that it is having the tendency to lose the electron, correct? And if it is having tendency to lose the electron, so we have just now we have studied it, okay, that the elements which are having tendency to lose electron, they are behaving like metals, right? Because metals also have tendency to lose the electrons, correct? And if they are behaving like metals, then we can say that they are having metal-like character or metallic character. Okay, so our answer is in front of you, metallic. Next, if an element has 7 electrons in its outermost shell, then it is likely to have the dash largest or smallest atomic size among all the elements in the same period. Okay, let's now try to correlate. If an element is having 7 electrons in its outermost shell, so which elements are having 7 electrons in their outermost shell? We know halogens, right? Just try to figure out this by taking an electronic configuration. Okay, fluorine 2,7. Okay, we know it is having 7 electrons in its outermost shell. That's why it is like badly craving for 1 electron. We have already studied these things. Okay, so you can just correlate by reading the question that whether you have figured out before previously any element which is having 7 electrons. And yes, we have studied about the halogens. Okay, they are having 7 electrons in their outermost shell. So now what they are asking us is such an element is likely to have largest or smallest atomic size among all the elements in the same period. So try to correlate this thing. See, fluorine, whether it would have largest or smallest size among all the elements in the period, okay, in the same period. So we know from lithium to fluorine, okay, atomic size goes on decreasing, and we also know that fluorine has smallest atomic size in the entire period. Okay, so what would be the answer? Then it is likely to have smallest atomic size among all the elements in the same period. So with this, we have reached the end of this video and the end of this chapter as well. And I hope you would have enjoyed learning with me. You would have understood all the concepts which I have taught to you in this chapter. But please do let me know in the comment section whether you have understood the concepts which I have taught you and whether you have enjoyed learning with me or not. And rest you know, LearnoHub matlab free hai par best hai. So stay tuned. See you in the next video with the next chapter. Till then, bye bye and have a great day.